ACID, which stands for atomicity, consistency, isolation, and durability, are four critical properties of relational database systems. I think any engineer working with relational databases such as Postgres, MySQL, SQL Server, Oracle, and even NoSQL databases or graph databases must really understand these four building blocks and fundamentals and first principles that build database systems. In this course, we'll go through these four properties in details, and I'll explain why each of these properties is critical to build and use relational databases successfully. Let's get started. So part of the work that we're going to discuss in this section is what is a transaction. Before we even start talking about these four properties, we really need to understand what is a database transaction at its core. And once we understand this, then we're going to jump into the first property, atomicity. What is it exactly? Why is it the most important thing to guarantee consistency? Speaking of consistency, we really need to talk about the transaction isolation. As I start multiple transactions concurrently, all of these are accessing my data, all of these transactions at the same time changing my data. What does it mean to for these transactions to be isolated from each other? What can they see? What should not they see? All these results into the consistency fourth parameter. I flipped the order here because I really believe talking about atomicity and isolation before consistency is actually critical to understand consistency. Because now if you have a transaction and this transaction changes something that I just wrote, then you're going to get a result that is unexpected. That affects your consistency. You get a data that you didn't expect it. It's bizarre, right? And finally, the most important one of the most actually, and one of the properties that a lot of NoSQL databases play with, durability. Some databases sacrifice durability for performance, and nothing wrong with that. It's just understanding the concept of durability, that when I actually commit a transaction, when I actually say save, this should really be persisted in a non-volatile place so that I can go back and read this data, even if my database is crashed, even if I lost power, I can still get access to my data. We're going to talk about all of these in detail. If you are interested in this thing, stay tuned and see you in the next lecture. Oh, forgot to mention one thing. By the end of this section, I added a little bit of a small quiz that I think you guys were going to enjoy. And obviously the answers are in the quiz. And even if you pick any wrong answer, I give you detailed explanation why that answer is not the actual correct answer, right? And we have all sorts of great discussions in this course as well. Now, let's jump to the next lecture. In this lecture, we're gonna discuss what is a database transaction. One of the most important things really to discuss this concept that you're gonna see everywhere when working with databases. A transaction really is nothing but a collection of SQL queries that are treated as one unit of work, right? And the reason we're treating this as one unit of work because the nature of SQL or the structured query language is my data is structured. It has many tables, so it's very hard to do everything you want in one query. And sometimes it's impossible, right? So that you really need to do one or more queries to achieve what you logically want at the application, I'm going to give example of that, what we mean by that. But effectively, that's what the transaction is. You begin a transaction, and then you do query through 4, 5, 6, 7, 8, 9, 10, and then you end the transaction. And that's one unit of work. This is logically one thing that cannot be split, and we're going to come to that. So an example of that is an account deposit. If you want to really deposit some money from one account to another account, then you really need to first select the money from the first account, check if that guy or gal has enough money in their account. And then once you select that, you do an update to that account to deduct the $100. And then the second update will be to deposit the money in the other account, which is increased by $100. So read, update, update. This is a transaction that is consisting of 3 different queries. Very, very important. So let's talk about the transaction lifespan. A transaction always begins with the keyword begin. That indicates to the database that, hey, you're about to start a brand new transaction with multiple queries in it. Okay. And then a transaction, when you are satisfied with all the queries, everything that you write is not durable. In a sense, it didn't actually get persisted in the database unless you say, hey, I'm satisfied. Please commit all the changes that I made during all the lifespan of the transaction. This commit tells the transaction to commit and to persist this thing to disk. And there are so many things here, really, questions that you can ask when it comes to commit, right? And think about the work that the database is doing to actually persist these changes. Let's say you execute 1,000 queries, right? As a database maintainer, if you build a database, how would you do it? Yes, the one you as a student listening to this, how would you build it? Because everyone else that have built databases might have done it differently than you might have do it, right? Because now, if you commit, like, what do? For all these 1,000 queries, all these 1,000 changes, do you actually write to disk with every one of these changes? Or do you wait and put all of these in memory, and then once you commit, you write everything to disk? There's pros and cons to do everything. The first one will make commit faster, right? The second one will make commit slower, right? But at the end of the day, there are pros and cons to any of these things, right? And this is what I want you to do here while listening to this course. Always think about what is really happening behind the scene. The basic bare bone fundamentals is what we are preaching here. And obviously, sometimes things doesn't necessarily go right? It's like, okay, I don't know, I executed 50,000 queries in my transaction. Bad idea, by the way. That long transactions are not recommended in general. But now I'm just, hey, I need to roll back. What does that mean, right? Roll back. That means, hey, all the changes, forget about it. Forget that I made all these changes. Do not persist them. But wait a second. Now, remember my question earlier about the 1,000 queries? All these 1,000 queries, as you execute them, do you actually persist them to disk? Because if you did, then you have to go and undo all this work, which is a lot of work. The second solution, right, where you write all these to memory and then commit to disk all of these changes, and you can play with this really. You can rollback will be faster because, hey, I didn't write anything. It's just flush anything in the memory, destroy it. Right? This is what you play with. Rollback, right? There is the undo, redo space for all these changes as well. That's how databases implement all this thing really differently. But as I am telling you this, I want you to think about these things. Think about how the database might have implemented these things. Very critical that you don't read it. Don't read how things are implemented because you're going to get polluted. I want your original thoughts, right? put it there. Let's have a discussion. Because one of you might have invented something that none of the computer scientists might have implemented. Yeah. All right. So obviously these are done by the user. Hey, I want to roll back right now. Hey, I want to comment right now. But things can go wrong, obviously, right? Transactions, unexpected ending, right? Because, hey, what if I am in the middle of my transaction, 20,000 queries later, I got a crash. The database crashed. What happened here? You need to actually roll back that. But the database crashed. How do you actually roll back? Well, the database, when it comes back, it better know to roll back this. So that's another code path that you need to code to. Yeah, databases are very hard to build. So think about all these use cases. And you can optimize your database and your use case based on that. Every database does it differently. Postgres does it differently. SQL Server does it differently. MySQL does it differently. Oracle does it differently. Each one optimizes on what they personally think, the engineers who built it, that, hey, I think I'm going to optimize for crashes. Or I think I'm going to optimize for commits. That's what Postgres does, by the way. Commits in Postgres are the fastest that you can get, right? Because they do that in a way such that any query that executed during the transaction, they try to persist this change. So Postgres does a lot of I/O, but their comments are beautiful, fast. So that's another thing, right? So another thing that I didn't mention here is, what if during a commit I get a crash? That's the scariest thing, right? If your commits are fast, then the chances that you're gonna get a crash are low. That's in Postgres. But if your commits are slow, I believe, if I'm not mistaken, SQL Server commits are slow. If you have a large transaction in general, then chances that you're going to get a crash during a commit are larger, and that's scary. Because, hey, I committed. What happened now? Is it committed or not? And that's the scary part. Let's talk about the nature of transactions. Usually transactions are used to change and modify data. That's what we always think about transaction. But actually, it's perfectly normal to have a read-only transaction. Hey, I'm going to start the transaction. I'm just going to read. And when you actually tell the database that, it can optimize itself such that, oh, this is a read-only transaction. And you might say, Hussein, what are you doing in a read-only transaction? Really? It's like, what? Why? Just read without a transaction. Have every query be its own transaction. No, actually, you want a transaction to maintain consistency. Let's talk about that a little bit. Let's give an example. You want to generate a report and you want to get a consistent snapshot based on the time transaction. What the transaction gives you, not only the beauty of this group of things that I need to do as one unit of work. No, you can also get it as a snapshot of the time of the start of the transaction. I want anything that I read is based on that initial time. That's the power of a transaction reading. Because anything you read, if something changed on by a concurrent transaction, you don't care. You want to be isolated, and that's another thing we're going to talk about. Yeah, we will learn more about this in the isolation section lecture. Stay tuned for that. Here's another example of how a transaction works. We talked about this in an earlier. Let's have this is a table, right? Account ID, and we have two fields, account ID and balance. The balance for account ID 1 is $1,000. The balance for account ID 2 is $500. And we want to send $100 from account 1 to account 2. Before we proceed with the slide, build this in your head. How would you build it? Stop this recording and then do it yourself and then move on. Obviously, the slides are available for you if you want to do it yourself. But effectively, here's what you do. You begin a transaction number 1, and then we select the balance from account, the account table where ID equal 1. So now I have 1,000, right? You check. First of all, in order to debit this account 1, I need to check if this guy even have enough money, right? We don't want to go imbalance. And that's part of the rules and the constraints that we put in place, right? You can put this in the application like what we're doing right now, and you can put this constraint at the database level so that it says, hey, this account, this balance should never go negative, for example, because it doesn't make sense to go negative, right? Unless you build your application in a way that negative means something, right? And if you ever see data that is negative, that is indication of an inconsistent data. And now I'm mentioning few things of the four properties, as you notice, right, as we discuss the transaction. But keep in mind, that's what inconsistency in data means. There are different kind of inconsistency that we're going to mention. All right, I'm good. I have more than $100. Let's debit my account. Update account, set balance equal balance minus 1 minus 100, where ID equal 1. Beautiful. Now we have $900. Now I want to, in the same transaction, update the account to add $100. There you go. Once we do that, we're happy with the changes. We commit the transaction. So both these are actually physically written to the disk, right? And we can argue where is it exactly written. That's a different situation and different discussion. So let's do a quick summary on this lecture. What is a transaction? A transaction is a collection of queries that are treated as a single unit of work. Transaction could change data or it could be only read-only as well, right? And a transaction is always started. This is something I didn't mention. A transaction is always started when you don't start the transaction. We start one for you in the database section, the database side. So if you execute, I don't know, just a normal update statement or an insert on the back end, the database starts a transaction implicitly and always immediately commits it, right? So we're always in a transaction, whether you like it or not. Some transactions are user defined and some are actually built and implicitly defined by the system. I'm gonna see you on the next lecture. Let's jump there. Atomicity is one of the 4 ACID properties that defines a relational database management system. And I always say relational, but really it defines any database system, whether it's NoSQL, graph, time-based, really anything. Atomicity is a very critical concept to understand. How about we jump into this lecture and discuss this beautiful concept? So talk about atomicity. Really, all the queries in a transaction must succeed. That is the definition of atomicity. We talked about what a transaction is really in the transaction lecture, and we said that all the queries in a given transaction is considered to be one unit of work. And that kind of defines what atomicity really is, right? It's like an atom. And until now, an atom cannot be split. I know there's nuclear fission that kind of contradicts that, but this thing was defined in 1970, and I don't believe they discovered fission back then. I might be wrong. But that's where atomicity comes into it. You treat this as an atom that cannot be split. All the queries in a transaction must succeed. If one query fails, what happens? If one query fails for any reason, a failed constraint, like the balance goes to minus negative, or a duplicate primary key entry, right? Or an actual invalid SQL syntax, that is a failed query. And what happens when you have one single, even if you had 100 successful queries in the same transaction, that one failure should roll back the transaction immediately. Because I said things went wrong. That's the rule of atomicity. So what happens if the database goes down during my transaction? I can't really roll back because the database goes down. What happened in this case, if the database went down prior to a commit, you didn't really commit the transaction. All the successful queries in the transaction should be rollbacked, right? Even if you had 100 successful queries in this transaction and you didn't really fail, your query didn't fail, but the database just crashed, right? So the next query didn't really fail, so the database will restart. So once the database restarts, that's when the database should detect that, hey, there was a failure technically, right? Because my queries didn't fail, but the database went down and I was mid-transaction and I didn't commit. These changes made by the transaction, if the database is actually making changes, should be rolled back. That's why I always want you to think about this as you read this, as I talk. What is the database doing in a transaction? Is it actually writing to disk? Right? I'm not going to commit. What if I don't commit? Do we go back to disk and remove these changes? All of this thing really is what makes or breaks a database. Right? And this goes back to most of the questions I receive, really, is what database should I choose? Well, really, you need to understand how these databases work, and based on your use case, make a choice. There are databases that before commits, any write you make, right, in the queries and the transaction, they are actually writing to disk. So they assume you're gonna commit, so they are optimistic in that nature. So when you actually in fact commit, I don't need to do any work because I committed. I actually wrote everything to disk. It will just write one bit that says this transaction is committed, and it's so fast, right? Other databases don't write anything, so the queries are so fast executing because they always write to memory. But the moment you want to commit, they have to go take everything that is in memory and then flushes to disk, and the commit will be slow in that regard, but the rollback will be as absolutely fast. You know, it all depends. There is no right or wrong. There's always a trade-off. Let's take an example. This is an example I talk about in my transaction lecture. Atomicity. So I have the same table, account table, balance 1,500, account ID 12. We want to send money from $100 from account 1 to account 2. What do? Very simple. We need to debit this account and credit this account. So minus 100 this, plus 100 this. And we have to do it in a transaction because these two should happen at the same time, right? So we start a transaction. We select the balance to check if this guy even have money. And they do, because the balance is greater than 100, because it's 1,000, right? Because that's the account 1. So yeah, let's go ahead and update the account. Let's deduct 100 and what? Database crashed. I did one change, and the second change I wanted to do, but the database crashed. We restarted the database. And let's assume this is a badly implemented database system. This is what we see when we restart the system. We see 900 here. What happened? So in this case, we just lost $100 in thin air. Right? That's really bad. That's really bad. Inconsistent. This is an inconsistent view. Not only you just lost actual money, that you have no idea where it gone because of technology, effectively, right? So after we restarted the machine, the first account has been debited, but the other account has not been credited. Very bad, inconsistent view. So lack of atomicity leads to inconsistencies, and we're going to talk about consistencies in its own lecture. This is really bad. We just lost data. The information is inconsistent. We talked about that. An atomic transaction is a transaction that will roll back all the queries if one or more queries fail. Well, in this situation, yeah, there is a failure, but it's not really our fault, because my other query, didn't even execute. So the database got restarted. So how do I know to roll back? I don't know. The database didn't even give it a chance to roll back. I can issue the command rollback. So the database now is responsible to clean up this garbage. It will say, okay, there was a running transaction, and it has to know that there is a transaction that has been running and it was crashed, right? So upon restart, we need to clean up, right? And let me tell you from my professional experience, right? I started working professionally back in 2005, and I've seen rollback that takes an hour, over an hour actually, for long transactions, especially in SQL Server. But I've seen rollbacks, not actual rollback commit by the user. No, actually the database says, wait, I can't even start the database before I roll back this stuff, because it has to go and clean up all the garbage that has been written, this half garbage that has been written, right? And this is the garbage has been written here. So we wrote that debit one account minus 100. We need to change the 900 back to 1,000 to get a consistent view. And that's where it all play. Some databases won't let you start the database before it's rolled back. They in recent patches and recent releases, they will say, okay, it's not really that bad. Let them roll back. Let them continue working on other tables, other databases. But this database now is it's in a rollback state. So CPU is getting hammered, right? Memory is getting hammered. All these things really as a result. The database should clean this up after a start. We talked about this, and we talked about how long this could take, right? And it really depends on how much you wrote and how long was the transaction. Long in transactions is generally a bad idea because of these things. Let's do a quick summary on atomicity. Atomicity is the idea of the transaction being one unit of work and that cannot be split. That's the property of an atom, at least back in 1970. If they figure fission, nuclear fission, then this is broken effectively. But you get the idea, right? So you cannot really an atom should be one unit and cannot be split, right? So if you have a transaction with 100 queries, all these 100 queries should succeed. If any of these 100 queries fail, all the 100 or anything that is successful in the query should be rolled back. And not only that, but you should, even in the case of a crash in the database, so that's not an actual explicit failure by the user, that should also roll back the changes. That was the atomicity lecture. I'm going to see you in the next lecture. Stay tuned. All right, let's talk about the third property in the ACID system. Isolation. Very, very critical and really underrated property. Not a lot of people truly understand the ramification of transaction isolation. So in this lecture, we're going to talk about isolation, and this is going to be a long lecture. So sit back, relax, grab a cup of coffee, tea, or your favorite drink, and let's go through it. So to talk about isolation, we have to answer this question. We have transactions, correct? And if it's a single user, that's fine, but we have many TCP connections to my database, if you support remote connections. And then each connection execute transactions. So there is a chance where concurrency can happen. Multiple transaction fighting over to write and to read the same pieces of data. And that's where isolation come into place. The question is, can my in-flight transaction see changes made by other transactions that are also in flight? That's the question that needs answering. Not only in flight, other in-flight transaction, even transaction that has finished. What if I am running a transaction and I'm querying, reading, and some other transaction committed a change? The question is, should I see this change? Well, it depends. Do you want to see that change? Right? There is no answer. There is no right or wrong. So as a result of these, you get a bunch of read phenomena, they call it, right? Very fancy name. And the main understanding of these read phenomena is these are usually undesirable. You don't want these. These are bad side effects, but we're going to go through them. We're going to understand whether are they. And if you run into one of them, you're going to see and you understand, oh, now I see what's happening here. And these are one of the nastiest things to debug, in my opinion. We're also gonna talk about isolation levels that were introduced to solve these undesirable read phenomena, right? So let's talk about isolation read phenomena. So what are these read phenomena? So the first read phenomena is called dirty read, and we're going to talk about them in details and with an example. But essentially, a dirty read is a read that you, as an in-flight transaction currently running, you read something that some other transaction has wrote, but didn't really commit yet. So there's a chance that this change that you just read could be rolled back, or it could be committed, or the database could be crashed, right? So this is called a dirty read. Anything that is dirty means that you wrote something and this write is not really fully flushed, not fully committed. It might change. And that's what is called dirty reads. Non-repeatable reads are reads that you are in a transaction, you read a value, right? And then in the same transaction, you read it again. And that sounds ridiculous. Like, what? Why would you ever read things twice? That's just dumb and inoptimal. But no, believe me, you do this all the time without you realizing. It's not about doing select ID from account and then doing select ID from the account. Not the same exact query. No, we're not talking about that. That's, it's a little bit odd to do that, but there are cases where you actually do the same exact query. But I'm talking about the different queries that yield the same value, and there are thousands of these cases. And one example is you're gonna read a value, but then you do a select sum, which also reads the value behind the scenes because it does a sum. These are different values, but they are dependent on the same entry that is in the database. So an unrepeatable read is when you read something and then the database tries to read the same value again, that changes, right? And this is called a non-repeatable. It was not repeatable in my own transaction. So that's what a read phenomena. Some people find this undesirable, right? I'm gonna show you an example of that. Phantom reads. Phantom reads are things that you cannot really read because they don't exist yet. I'm going to give you an example. So example with this is our range queries. Like let's say, hey, select all the activities between this date and this date, right? When you do this range between this and this, right, you get a number, right? You get a certain values. But then let's say someone inserted a new rows here. It's a completely new row. It's not really a non-repeatable read. You didn't even read it. It's just something that is inserted that satisfies your range query now. Now, if you do that and you do another select, right, you're going to get that phantom new row and you're going to get that read. And that things might go really wrong with that. And that's called phantom read. So you got certain result in the first situation, but the second one, you got a completely different result. So it's not really completely non-repeatable read. It doesn't qualify as a non-repeatable because you didn't really read it in the first place, right? You can't quite catch it. I'm doing this with my hand, but you can't see it. I'm doing this with my hand. The fourth one is really lost updates. That means I wrote something, but before I commit this write, I tried to read what I wrote. Well, this is very common because if you're on transaction and you write something and you turn around and read that something, that's completely fine because you are in your own bubble. You can read what you wrote, but other transactions usually can't. Depends whether dirty reads are enabled or not. But some other transaction can actually change what you wrote. So if you turn around and read what you just wrote, it's just lost. And that's called lost updates. We're going to talk about when that actually can happen and how to circumvent this. All right, dirty reads. Let's take an example. So we have a sales table here and we have 3 columns. product ID, quantity, and the price. Product 1 has sold 10 quantities, and each is $5. So the total price is what? $550? $50. So we sold $50 worth of product 1. Product 2 is 20 quantity, $4. So the total is what? $80. So what is a dirty read in this case? You begin a transaction as usual, and you start this query. You select the product ID, and then the second column is an actually expression. You multiplying the quantity times the price because you want to see the total, right? From sales. That's generally a bad query. Not because we're doing an expression, but because we don't have a where clause. But we're explaining things here. So as long as I tell you that this is bad, because if you have billions of sales, now this is going through the whole entire table. You have to have always a range. You have to have a bounded query. I always say it's bounded, and the reason is it's unbound. This is an unbounded query. That means there is no bounds. It's just forever. It goes forever, right? Yeah, we have 2 rows here, but when things work with 2 rows, it doesn't necessarily work with 100,000 rows, right? But yeah, we got the idea, right? So we have what we're gonna get is a product 1 is 50 and the product 2 is 80, right? That's what we got. And this is the list. I don't know, maybe I'm generating a report, a sales report. And now another transaction started while this is actually running. So these are in parallel now, right? So this started and this is now started. We selected this. We read the actual values that are currently in the table. Transactions 2 started, and right after this guy read the values, it actually made some more sales. Some people made some more sales on product 1. We added an extra 5. We sold an extra 5 products, right? So now what will happen is now it's 15. Okay. Now look at this. We're doing another query, but now we're just we want to sum all the sales, right, regardless of the products. What do you think the value should be versus what do you think the value will be based on a dirty read configuration? Look what will happen. We're gonna get 155. Why? Because if you multiply this 15 by 5 plus 80, which is good, this didn't change. So the original sum is actually 130 if you think about it, right? 50 plus 80. But we added a $25 worth of sales. So if you add that, you're gonna get 155, which is technically not wrong, but if you within the same transaction, this is inconsistent, because if you actually print this in a report and you went to the manager, says, okay, oh, product 150, product 280, and then you print it all the way down in the summary, you printed the sum as 155, they say, what are you doing? That's just wrong, right? And why did we do that? Because we read a dirty read. This guy didn't even commit, and yet we read the value. You notice that the line of the commit didn't even happen. Now we commit my transaction, which really didn't change anything, but we're just reading just to tell you that the transaction has terminated. But now this guy just, hey, you know what? Never mind. I'm going to roll back. Because, hey, we didn't really actually made five sales. Roll back. So no, this is actually worse. You read a dirty read, and that read has gone, right? And that is really a problem. You get an inconsistent results. So let's talk about non-repeatable read here. Same configuration here, 1050, 10.5, 24, and then we're going to begin a transaction. Now we're going to select the same exact thing. We're going to get product 1, 50, product 2, 80. So what is a non-repeatable read here? Another transaction begins, but look at that, the arrow is shorter. I made the arrow shorter. Why? Because here's what I'm going to do. This time, I'm going to make the sale, and guess what? I'm going to actually commit the change before the second transaction finish it, or before the second transaction actually made the second query to do the sum. Look at this. So we actually persisted. This is not a dirty read. This is an actual valid write and valid read. So the value is actually 15, but we read the value prior that change. So now, what should we do? Now I do a sum count price from sales, and guess what we're gonna do? We're gonna get the exact same wrong result. We get 155 when it should have been 130, right? That's the actual result that is desirable. So now this is not really a dirty read. This is an actual committed read. But the problem is this was a non-repeatable read because you read the values here and you read them kind of again, right? But you read them through an aggregation function, right? And as a result, you got an inconsistent value. And you might say, Hussein, in this case, I don't want non-repeatable read. Not all the time. Because we're going to come to that. But fixing this is expensive. Fixing this so that you read always the same version of the value here is not easy. A lot of databases support it through MVCC, but it's not easy because now you have to keep a version of the product one at the original state. That's what Postgres does, by the way. Postgres always, any updates, creates a new version of the row. It never changes the same value. While MySQL and Oracle, and might be also SQL Server, changes this. The final value changes to 15, but it keeps another table called the undo, right? I'm writing undo here. I don't know if you can see it. But the undo stack keeps an actual writing to disk, a place where all previous values. Oh, product one, by the way, it used to be 10, it turns to be 15, right? I don't know. It keeps the delta changes. So now, if this guy wants to read in Postgres, it will read the original version. It just keeps a version pointer here. So there is another row, product one, version 2, right? Version B, for example, so you don't get confused. But in MySQL, what will happen is it cannot read this. It has to go and crack open the undo log and then read their values, and that could be expensive for long-running transactions, right? Because it cannot trust this latest value anymore. So yeah, this was just a short explanation of isolation, but we're gonna come to that. Yep, and then we commit, and obviously nothing changes. Bad. Non-repeatable read can be bad. So it really up to you, guys. You cannot just go by this example and say, oh, I'm fine. No, really comes back to what are you trying to build, and then just understand this problem and say, hey, I'm fine. I'm even fine with dirty reads, because I don't think anybody's fine with dirty reads. Dirty reads is the worst. But I have actually built an application where I relied on dirty read, which was a very bad idea. I regretted that later. Let's talk about phantom read. So phantom reads result from range queries. Anything that can potentially give you one or more results. Pretty much, phantom read always happen, if you think about it, if you have a where clause. I can't think of an example where phantom read could not happen, to be honest. So same configuration, sales. We begin a transaction. We do a select quantity price sales. And this time, I'm reading this product, 50 and 80. Transaction 2 started. Now, it didn't really update. It inserted a new product, completely new product. Right? So now if you insert a new product, well, that's fine, because in this case, we didn't really read this product, but get this. It actually commits it. So now we have $10 quantity of product 3 at the price of 1. So an extra $10. So now what we do here in your original transaction, you're going to do a sum quantity from sales, which it doesn't have. It's an unbounded query. There is no bound to it. So that means we're going to, unfortunately, sum all of them include product 3. Yikesy. So we get 140, which should be 130. We read a committed value, nevertheless, not really dirty, and that just happened to show up in our range query, right? It's not really a non-repeatable read because we never actually read product 3 to begin with. In the previous one, we read these two values and they changed later, okay? So, and why are we differentiating between these two is really the implementation when it comes to it. Like if you really want to know, you guys are interested, it just comes down to locking. In non-repeatable reads, when we read something, we want to guarantee repeatable reads. Anything that the transaction reads just obtains a shared lock on it. not really a shared lock. It's one kind of locks. I'm going to talk about locks in this course as well. And then if it just makes sure that this read doesn't change for that transaction. That's what it makes sure of. But how does it get rid of new rows that has never been read? How does it get? You cannot even see the row to lock it to prevent it from changing. That's what phantom reads. You cannot grab it, right? It's phantom. So last update. Let's talk about the last read phenomena. So same thing here. We're going to begin two transactions in parallel concurrently. We're going to update one of these guys, update the quantity to increase to, let's say we added a $10 sale, 10 units of sales to product 1. Now, from 10, it turns to 20. Transaction 2 updated the same quantity to add 5. But guess what? This quantity now, it's reading the original value because they started at the same time. So both of them actually read quantity as 10. So this guy is also 10. So now what it will do is it will take the 10 plus 5 and then store it into the product. So now we have 15. So now we lost the value here. Okay? And that's what happens in this situation. So now we commit the transaction. Transaction 2 was faster, so it committed, and now we have the value 15. And now transaction 1 assumes that it made the sales. It will do the sum, and we're going to give you a completely different result that is absolutely wrong, because it should have been 180, but we got actually less result. Why? Because our update was actually overwritten by another transaction, and as a result, it was lost. One of the nastiest thing. And this can be solved basically by actually locking the row. So hey, if someone row level locks are very popular here, we're going to talk about them here. It's like, hey, I just changed this. I don't want anyone else to change the same row. There's no point of it. Let me finish and then release it. And then once I'm done, you go your own merry way. All right. We talked about read phenomena. We need to talk about isolation. I know this lecture is a little bit long, guys, but there's a lot of information here. Feel free to ask questions and to understand this better. So isolation levels for in-flight transaction. What are they? So we're going to talk about many isolation levels. That were invented to fix those read phenomena that we talked about. So when I try and start my transaction, you set this isolation level. Using keyword, I believe, set isolation level, literally in a transaction. This is the SQL command for it. So, hey, I want to start a transaction with read uncommitted. That's the first one, which I believe no database supports except SQL Server. Read uncommitted just means no isolation. I want to read anything you read is visible by anybody outside that changes this value. Right? It just read uncommitted is related to the transaction itself. So it means no isolation. Any change from outside is visible to the transaction, whether it's committed or not. That's what's called read uncommitted. You can read uncommitted values. As a result, you can get dirty reads here. Bad, obviously. But if you think about it, it's technically fast, right? Because I don't really need to maintain anything. It's questionable because the implementation, you don't know what the implementation is. You just assume from theory that it's fast, but could be not. Read committed. This isolation is one of the most popular isolation levels out there. And so a lot of databases optimize their engines for read committed workloads, which means each query in a transaction only sees committed changes by other transaction. And we talked about that in the examples, right? So now if there's a transaction that makes a change, right, while I'm reading something, I'm not going to see this change unless the transaction commits it. Once it's committed while I'm still running the transaction, I'll be able to see that change. You might not be happy with that. You say, hey, this could get inconsistent, but just understand that this exists. And I believe this is the default isolation level for many databases. Just understand that if you have a long-running transaction, anything that has been committed will be picked up by a transaction. This could be bad. Repeatable read, which is the isolation level, was invented to fix the non-repeatable read. Right? Non-repeatable read is just bad read phenomena. Repeatable read is the isolation level to make the read repeatable. That means as I read and I read it again, it's not going to change. I can read it 1,000 times. As long as I'm in the same transaction, the value will not change. Let's read this definition. And by the way, I rewrote this definition based on my understanding. You will not find these definitions in the web because, frankly speaking, computer scientists always complicate things because they added a lot of jargon for some reason, right? So based on my personal experience and professional experience working since 2005, this is what I give you. I give you things that are practical, that you can touch and feel, right? Fix the typo there here. So the transaction will make sure that when a query reads a row, that row will remain unchanged while the transaction is running effectively, right? So that's what it means. Only when the transaction actually reads a value, reads an object, reads a row, reads a column, then we're gonna make sure that as long as this transaction is running, that value will never change. But if you didn't run it, if you don't read it, we're not gonna copy a version of that row. If you get my point, right? Because how do you implement something like that? Think about what the database is doing for you. There is cost for everything, and this is a cost. If you can take a snapshot of the entire database if you want, and that's another isolation level, by the way, called snapshot, right? But that's also expensive. There's the thing, snapshot. Each query in a transaction only sees changes that have been committed up to the start of the transaction. It's like a snapshot of the whole database at that moment. This is guaranteed to get rid of every read phenomena. This repeatable read doesn't get rid of phantom reads because we saw that phantom read just sneaks in. It's an insert. We never actually read a value to lock it or to obtain some sort of a lock so that we can version it. We didn't even get to do that, right? Snapshot isolation, this is what I read at that stage. And Postgres repeatable read is actually a snapshot isolation. It's just everything versioned. So if you start a transaction, you kind of timestamp which version you are in. And then as a result, you're always going to read this version. So even if new inserted rows show up, you will not pick them up because the database will filter things based on your version effectively. And that's the power of the snapshot isolation. The final one, or basically the slowest, if you think about it, is serializable. That means there are no concurrency anymore. Just each transaction is almost physically, database is implemented differently, but as if they are serialized after the other. So if there are 3 transactions starting the same place, they will be serialized based on, now this depends on the linearizability and complicated stuff like that. Which one goes first is the question that the database tries to answer so that you get almost the same result. And obviously, I talked about that. Each DBMS implement isolation level differently. Don't over stress with these isolation levels. Just understand that they exist. Most of the time, you're never gonna run into these complex situations. But if you do, know that these things exist, especially with a lot of users changing and reading at the same time. This is when you need to know about this at least. I took this from Wikipedia. I like this table a lot. It doesn't have the snapshot isolation, but if you look at this, you can see that read uncommitted, everything may occur. With all the read phenomena occur. This read committed, everything can happen except dirty read. You cannot get dirty read because, hey, I'm reading committed stuff. Repeatable reads, you don't get dirty reads, you don't get lost updates, and you don't get non-repeatable reads as well. All right, because we fixed that with repeatable read, but you still get phantoms. But in serializable and also snapshot, you don't get any of this. It's all fixed effectively, right? And there is a slight difference between serializable and snapshot. right? Serializable is effectively just slows things down if you think about it, right? Because it just serializes things. While snapshot takes a version of the database at the start of the transaction. Now, when I say a version of the database, I'm not talking about actual backup, right? It's the database have to implement this in a optimized manner. Make sense, guys? Let's talk about a little bit of database implementation of isolation. Each DBMS implements isolation level differently, of course. There is the pessimistic. Did I spell this right? Pessimistic approach, which is this means the pessimistic concurrency control. To be specific, it means I'm going to use locks, and I'm going to dedicate an entire section lectures talking about locks. When you get to that, you're going to learn more about it. But effectively, I'm going to obtain our row level locks, table locks, page locks. Table locks, that means any change I make, I'm going to obtain a lock in the whole table. Very, very expensive, by the way. I run into a lot of situations where my transactions lock the entire table, called lock escalation. It's escalated the row to a table lock, and then all transactions were just pending, trying to change other values, and it couldn't because the table was locked. Page lock, the actual logical page that contain the changes are locked. This is especially true in case of clustering. If you want to cluster your table, again, we're going to talk about that as well. And then these pages that you write to also have certain locks. So effectively, there's a pessimistic approach. Lock, hey, I'm changing, lock it. Don't let anybody touch this. So if you lock a row, only that row won't be able to touch it. You're going to see some examples when I showed in Postgres and MySQL that when we try to update something, it will succeed, but another transaction when we try to update, it will just sit there and wait because the row is locked. Optimistic usually don't use locks. That's the other approach. That means there won't be any pending transaction. So also, not only that, so nobody will wait on the other, and also, the benefits of this is the lock management, which is extremely expensive, by the way. Because how do you know that a row is locked? You have to maintain it in memory, right? You have to keep track. The database has to keep track. Oh, this is locked. This is not. This is locked. This is expensive, especially row level locks. If you have like 700,000 table rows that you need to lock, this is expensive. So optimistic, a lot of people prefer this approach where, hey, I'm not going to obtain an actual lock, but I am going to just let things play by ear. And when when transactions start stepping on each other, boom, I'm going to fail the transaction. And the user should just retry. And the error is called usually a serializable error. You get it's like, hey, something changed at the beginning of the transaction, so just retry the transaction. NoSQL databases prefer this approach to locking because locking is expensive. Repeatable read locks, I talked about that a little bit. Repeatable read locks the rows it reads, but it could be expensive if you reads a lot of rows. Postgres implements repeatable read as a snapshot. We talked about that, right? Snapshot and repeatable read in Postgres are identical. It's the same thing, right? This is why you don't get phantom reads with Postgres in repeatable reads, where in other databases you get phantom reads with repeatable reads. And spoiler alert, that's part of a quiz. Serializable are usually implemented with optimistic concurrency control. Because if you actually truly do serializable, then your database is gonna be so slow, right? Because what is serializable? Just one after the other, right? So if you, that's why a database is implemented with optimistic concurrency control. You can also implement it pessimistically if you want to with select for update. Hey, I'm gonna select this, but I'm gonna lock it. Right, that's what you do. So let's summarize the isolation. Isolation is the result of having the transaction run in complete isolation from other concurrent transaction. As a result, we get read phenomena, and we have a lot of isolation levels that have been invented to fix read phenomena. Let's jump to the next lecture. Good job, by the way, finishing this lecture. Good job. We talked about atomicity. We talked about isolation. We talked about what is really a transaction, which is really the most important thing here to understand before jumping into these properties. And then we really need to talk about consistency, which is one of the properties that were traded off in different platforms. When I say different database platform, I mean NoSQL versus relational versus graph. Consistency played a lot of role there. So some databases sacrifice consistency for speed and performance and scalability. I'm not going to talk about all that stuff, but consistency really, what do we mean by consistency? And in order to understand that, really, consistency are really twofolds. There is what I call consistency in the data itself, which represent the state of the data that is currently persisted. Okay, so what do you have actually in disk? Is what you have in disk consistent with the data model that you have? And we're going to talk about what does that mean. And there is another consistency, which I call consistency in read. So your data might be consistent on disk, but the reading of the data becomes inconsistent because you have multiple instances and they are slightly out of sync. So this applies to the system as a whole. So if you have like many shards or many partitions or many database instances, right? This is applied to the system as a whole. As a user, I don't care what database instance I have. I'm just issuing a read. That read better be consistent. And consistent in data is in a given cluster, in a given data instance, what is going on there? Is my data even consistent at that level, right? And let's take some examples. So let's talk about consistency in data. This is really defined by the user, right? This is something that the user defines, and by the user I mean the DBA really, or whomever builds out the data model in the database, right? And it really comes down to most of the time enforcing referential integrity and foreign keys in the database, right? I know some people coming from NoSQL don't have these concepts, but believe it or not, you do have referential integrity, whether you like it or not. You might have a document here that is referring to another document, and the moment there is a referential, there must be integrity in this reference effectively. We'll take an example that clarifies what that really means. And what also ensures consistency in the data is, guess what? Atomicity. If we had a crash while we debited one account and then restarted the database and the account remains debited half, right? We just lost $100 in thin air. That's an inconsistency in data. The data is just persisted wrong. It's corrupt, as we call it, engineers. There's corruption effectively. You corrupted your database effectively. That's pretty bad. Isolation also can result in inconsistency of data, because you could, we talked about that in the isolation lecture, where you can issue a read and you get a bunch of data back, right? But then you issue another read and you get different results based on your isolation level, and that leads to inconsistent result. So yeah, your data might be correct, but it is changing, consistently changing, and this change is giving you a different view. As a result, your view of the consistency is getting wrong. Here's an example. Let's assume you're building some sort of an Instagram data model here. So you have the pictures table. You have an ID. You have a blob of the picture, binary large object, and the number of likes that this picture got. And then we have a tracking table that says, okay, John have liked picture 1, and Edmond had liked also picture 1, and John also liked picture 2. So you have certain referential integrities here. What is that? And it's defined by you as the DBA, whoever built this, because the number of likes here better be equal to the sum of these guys, right? Because if I do a select count from this table, where picture ID equal 1, I better get 2 likes, and this should be equal. And this is basically the consistency in data. If this is inconsistent, then bad things can happen. Who cares about if you're out of sync with the number of likes? People give that up because really nobody cares. Nobody's gonna browse Kylie Jenner's 1.8 million like picture. Nah, nobody's doing that. But you get the point. This is one example, right? Another example is if you've seen an entry here to a picture that doesn't exist anymore, right? That's also inconsistency, right? And this is what we really mean when we talk about consistency in ACID transactions, right? We're talking about the ACID consistency here. Talking about the ACID consistency here. So I'll give you a few moments here to spot the inconsistencies in this data model. Take a look. So you might have already spotted picture 1 got 5 likes, but if you actually query the likes table, you can see that picture 1 only got 2 likes. So something got out of sync. This is an inconsistent referential integrity. Another referential integrity inconsistent data is you have Edmond liking picture 4, but if you actually want to get the actual picture in the pictures table, picture 4 doesn't even exist. So that's also an inconsistent result. So someone deleted this picture, but they didn't have a cascading event to delete the likes picture effectively, right? Leaving those effectively orphaned, right? And you can have the database do these constraints, or you can have it do it at the application level. It's really up to you. But this is what we mean by inconsistency here. Is that what all it is? No, really. Consistency in read is another thing that can happen, right? Let's take an example. You have a database system here, and you can look at this as a single database or multiple, doesn't matter. But you're talking to one reverse proxy effectively that proxies that request to the backend. So you're updating value X, and now the database persists the value X, and now the next read after this thing commits must give you the value X. That's what it means by consistency in reads. You might say, Hussein, that's just obvious. Well, not all the time. Let's take an example. If a transaction committed a change, will a new transaction immediately see the change? That's what really boils down to, right? If I committed a change to a database and then I issue a read immediately and I don't see the change, then you are inconsistent effectively, because you just read something that is not really the value that you're supposed to get, and it affects the system as a whole. And what is an example that can get to? Is basically when you have a master or a main replica primary database, and they have a multiple worker database, right? And you're syncing the changes to the backend. And I have an entire section talking about replication, so check that out when you finish with this lecture. But effectively, as you write to the primary will sync back the changes to the replica. And if you read in the replica, you might get an old value. And that's what we mean by inconsistency here. So that's why it affects the system as a whole. Relational and NoSQL databases suffer from this kind of consistency. And even NoSQL suffers from the first type, if you think about it, right? It still does have this idea of inconsistent result in the persisted model. If you don't ensure referential integrity between your, MongoDB documents, you're going to get the same exact problem, right? Right? If you have users and a followers list, and I don't know what you do, you have to ensure the referential integrity effectively that you set, the rules that you build. And then we come back to this marketing term that is called eventual consistency. It releases, okay, which is really what means is, hey, I'm not consistent, but I'm eventually going to be consistent. I kind of torn on this term, to be honest. I'll give my thoughts in another lecture, but in a nutshell, most of the things that are currently not consistent will get eventually consistent. But that is very important to understand, because in the consistency of data, if your data is corrupt and referential integrity is broken, there is no eventual consistency coming out of that, right? Because hey, the data is just corrupt. You have 5 likes, but only 2 records that represent the likes. That is no eventual consistency coming from that, unless you have some sort of a repair post batch job that fixes that. But that's what we mean by eventual consistency, is only really to the reads, because if you continue issuing a read, you're going to get old values, but eventually you're going to get the correct value. That's what they mean by eventual consistency. And there is many terms here: eventual strong consistency and eventual weak consistency, and there is so much stuff you can go into this. I can really make an entire course just talking about eventual consistency. So it is valid in certain cases, but it's been invented to kind of differentiate between the corruption that can happen to your data effectively. So in summary, consistency are 2 types: consistency in the data, which are enforced by the referential integrity, right? Things that is persisted in the data, and there is no eventual consistency coming out of that, because your data will become kind of corrupt based on what you define by corruption here. And the different type is consistency in read. The consistency in read is when you update a value and then a transaction tries to read that value after it was committed, you get the old version, and that's an inconsistent result, right? So it was most databases heal from this kind of inconsistency by eventual consistency. So that means as the replication process completes, you will eventually get the final result effectively from that read, right? And this can be enforced by something called synchronous replication, which I believe I talked about in this course. Yeah, synchronous replication versus asynchronous replication. One is slower than the other, but one give you strong consistency and the other give you eventual consistency. At the end of the day, it's all comes down to what really you want effectively. And eventual consistency is something both relational databases and NoSQL suffer from. So that was basically a summary of the consistency. How about we jump to the final lecture, durability, one of my favorite.